So let me share my screen. Okay, so let's get started. So I will first show you a couple of slides. So I will first show you just a few slides on machine learning before I then go to an introduction into R and RStudio, and also a few slides about managing data. Then we can have a short break or question round before we then go to the more practical part where I do a live demonstration of two data sets I'm going to analyze, one with linear regression and the other one with logistic regression. So these two data sets are real data. So they consist of data with real patients. So the first one is about blood pressure from the CDC. So that's a continuous outcome. And the second data set is a cancer data set. So all the materials are online on OSF. So here you have the link with the ID GRBCY. So when you go there, you see all these files here, and you can just click here and download the script as a zip file. So there are two data sets and a R Markdown file to analyze the data. And you can also see my slides here. If you want to do the analysis your own, you have to have R installed as well as RStudio. Then you could also do that your own. But I will show you, I will guide you through all the analysis. So my talk is basically aligned to this book, Practical Machine Learning in R, by Benganga and Chappell. I will cover parts of chapter 1 to 5 and also chapter 9. So first, as I prepared this talk, I was thinking about what's actually the difference between statistics and machine learning. So I work a lot in statistics, but I also had some project where I applied machine learning. And I found a paper by Bedstock where it shows that, or where he basically states that statistics is to draw population inference from a sample. So you have your point estimate and the confidence interval where you test the hypothesis. So how likely is the data under the null? So that's kind of informal definition of the p-value. So an example would be to assess a treatment effect or treatment efficacy in a clinical study. While in machine learning, the goal is to find generalizable predictive patterns to forecast unobserved outcomes in new data. So for example, a predictive model for a screening test for cancer, for example. But the distinction is not that easy. And here I will show two, let's say, simple or established techniques, regression and logistic regression. And this is actually, I will talk a lot about statistics today. And maybe machine learning is a lot of statistics and there is much overlap. One distinction maybe is that machine learning is more exploratory as compared to confirmatory research. There are also some other concepts where I'm not going to talk about, so I will not talk about AI, artificial intelligence. So the only experience there where I have in artificial intelligence is from some movies that I watched. So a great example is Blade Runner, of course. I will not talk about deep learning. So deep learning are more complex machine learning methods, such as neural networks. So what I will cover is some basic techniques in machine learning, regression, where here you see also the word statistics again. So apply statistics to discover new knowledge by generalized examples. So there is a distinction between supervised and unsupervised learning. Surely you all probably know that. And I will focus on purely supervised learning, where we have labels. While unsupervised learning is when there are no labels. So one way to see this is that supervised learning helps us to assign new labels to known labels to new observations. That's what we are going to do today. So, and unsupervised learning helps us to discover new labels. We start with a training data set. We apply some machine learning algorithm to generate a model. And then we apply that to some new data and make predictions. So how do we then assess these predictions? So when there is classification, as you will see in our cancer data set, where the outcome is whether someone has a malignant tumor or a benign tumor, we can create a confusion matrix. So basically we know in the test data set whether a patient had cancer or not, and we have predictions which tell us whether someone has cancer or not, and we can just create the confusion. So each case can be a true positive or a true negative, and two types of errors that we can make. So type 1 error is the false positives, and type 2 error are the false negatives. So for example, with the cancer example, that would be someone who is declared that this person has not cancer, but actually the patient has cancer. So that would be not a good outcome. So in the cancer example, the false negative rate is probably more concerning than the false positive rate. And we can then calculate the false positive and false negative rate. And this is also closely related to specificity and sensitivity. But US medical colleagues are really all aware of that. So this is really important in diagnosis and medical testing. The other thing is when you have not a dichotomous outcome, but a continuous outcome. So for example, blood pressure. So we have some blood pressure, which we know are the ones that we have measured. So the actual blood pressure measurements, and you have some predictions. And so we can compare these values. So here you see the regression line from, and the actual values are here, the orange ones. And our predicted values are obviously on the regression line. And the error that we do is the difference here between the true value and the one that we have predicted. And a way to quantify that is to square all these distances, so the red lines, and sum them up. That's then the residual value. So these differences, the red line, these are the errors, or they are called the residuals. An important aspect is, of course, to partition the data set. So we generate a subset from the data set, which is the training data. And then we have a subset that is the test data, where we then validate our model. But actually, it's a good thing maybe to even create 3 data sets. So we have a training data set and a validation data set, and we iteratively tune our parameters or change things like adding a variable or removing a variable, and then always check with the validation data set, to kind of develop a model. So you need to develop a model. But we hold out the test data set. That's really important. So this has to be unseen data. And then at the end, when I'm done and I have my model, I then test this model once on the test data, on the unseen test data. That's also called the holdout method. There are cross-validation methods as well, but I'm not going to talk about that. Okay, so with that, I want to move to R. So R is basically a programming language in the first place, like Python, but it's a language dedicated to the statistics. It was created in 1992, and it's free and open source software, so you can download that and share it. There are lots of packages available, so you can load these packages to have more features, and they are available on CRAN, so the Comprehensive Archive Network. You can install these packages from within R, which is really nice. So it's a nice package management system and makes things much easier, like dependencies between packages, so they are resolved. And here's the link to the website where you can download R. But R is basically what you see in this terminal. You type R, and you hit enter, and then you are in a small little terminal window where you can do your calculations. So I use that, you know, to pay my bills and do some simple stuff compared like to using a calculator. But you can do much more advanced stuff in this window. You can do a t-test or whatever you want. But it's much nicer to work with a graphical user interface. And that's why RStudio is for. So that's an integrated development environment, and it's also free software, and it's just much nicer, you know, to work with RStudio. Even though I have many colleagues that are absolute experts in statistics, and they just work in the terminal because you can do anything, you know, there. But for beginners and also myself, I work in RStudio every day because it's really nice, and I will show you then in the second part. There are different sections in RStudio. So you have like 4 sections. So here, this is like the editor where you write your script or your R notebook. Here you have the console, which you have seen on the last slide. So you can still here interact with the variables directly. And here you have some other parts. Here is the environment where you see all the variables that are in the workspace or are like in the memory. Like here's a variable called data that contains all the data. And here on the bottom right, you have some sections where plots are displayed, or you know, when you type help of a specific function, it will also be shown here. The way you install packages, and that's what you have to do at first when you want to run my calculations, is use the command install packages. For example, ggplot2, that's a package for making nice figures. But once it's installed, you also have to load it to have all these functions available. So that's then with the library command. And keep in mind that, as you can see with the library command, you don't use these quotation marks, but with install packages, you have to use the quotation marks. As in any programming language, there are data types like numbers. There are even different data types for within the numeric range, like integers or floating points. Then there are a logical data type, which is true or false. We have characters, like patient IDs, for example. But we have also a special type of characters, which are factors. So they are restricted. So in this case, we only have here 2 possibilities, patient or control. So there are 2 levels. There can be like 4 or any levels. But this is a great way to work with data, because when you do like a Boxplot, for example, or you calculate the mean, you can then calculate the mean per the different levels of that factor. And that's really nice to have this data type. Then there are missing values, which are NA in R, That's important. They shouldn't be like 0 or, you know, empty or blanks. You know, there is a dedicated data type for missing values. And then there are, of course, also something called vectors. So that's like a collection of elements. So like a collection of, you know, odds ratios or a collection of names like here. So this is a vector of the size 2 because there are 2 elements like Joe and Jane. And you use this special function C to initialize such a vector. And when you want to access the vector, you use you index. So the second element, for example, of this vector names will return Jane. So keep in mind that to initialize a vector, you have to use the round bracket, while to access elements, you have to use the square bracket. Now, to extend that to the second, to 2 dimension, like a table, for example, the first dimension is always the rows. The second dimension is the columns. So this would be the element at the first row in the third column. And when you leave it empty, so after the comma, there is just empty. This means all. So, so here you would show the first row, all the elements of the first row. And here you would show all the elements of the third column. So now I go a little bit to data management and address some important topics to keep in mind. One is missing values, how to deal with that. I will not say too much about that because in our example, fortunately, we don't have missing data, but it's a really important topic. And, you know, someone else could probably give a whole talk about missing values and to address that because it's really important. So there are really, maybe one can say that there are more simple techniques like random imputation or mean imputation, but generally that's not recommended because with, for example, mean imputation, so you just take the mean and of all the across the variable and impute that into the missing values. This doesn't add any new information. So more advanced techniques are relevant, like multiple imputation, but that's quite a topic of its own for another session. Outlier is also an important thing to consider. So that are data points that are significantly off from other observations. So how do you deal with that? So in the first, well, in the first place, outliers, they should not be excluded. They are legitimate data. If it's not like some error measurement. And we will look in the practical then. I will show you how to examine outliers by something called influential point analysis, where we can identify values that are off and could potentially influence our main analysis. Now, another thing which is relevant is class imbalance. So that's when the proportion in your examples is different of the class. So in our example that we look at later, that there will be imbalance. So we have, for example, a smaller amount of patients with malignant cancer compared to benign cancer. So ideally this distribution, so it should be like 50-50 in the training data. Because if not, there could be a potential bias in terms that you favor the majority class. So there are ways to fix that imbalance. For example, collect more data, use different methods which can handle that problem. Or what we are going to do is to resample data. So we change the class distribution of the training data set. And there are 2 ways to do that: undersampling, so we select fewer cases from the majority class, or what I'm going to show you is to oversample. So we create more copies of the minority class. And we use more kind of an advanced technique like called SMOTE, synthetic minority oversampling technique. This is a popular approach to generate minority examples. And then we have a balanced training data set. But the test data set will not be balanced, and we will test our model that we trained on the imbalanced data, training data, test data. Another important topic is transforming of data. So there are different things different methods you can transform the data. Like I'm going to show you how to do a set score normalization, where the mean is then 0 and standard deviation is 1. But there are, just to have a complete list, well, it's not a complete list, but I kind of also listed some other techniques that are sometimes popular. Then the two methods, just very briefly, the two methods that we are going to use is a multiple linear regression. And in R, you can use the LM command, and you have the outcome here on the left side of the formula. So that this part here is the formula. So it's looks very similar to the regression equation here. So the x's are then our independent variables, and you kind of add them with a plus. So let's say if our explanatory variables or independent variables is age, we type age plus, let's say, gender plus tumor size or whatever. And then here we also specify the data. And then we will then get our beta estimates, which are unknown and which we are interested in. I already explained the residuals, so it's important to briefly look at the residuals when you do a regression. I will show you how to do that in R. It's called residual diagnostics. So they are some assumption in regressions that need to hold or need to be met. They need to be zero mean or mean zero. They should be normally distributed. And there is something called homoscedasticity of the residuals. So that reflects that, for example, with blood pressure, that when we predict the values of people with high blood pressure, the errors should be not like inflated. So the errors or our residuals should be like similar across our predictions. For model evaluation, there is, we can calculate the residual standard error. So that's basically the standard deviation of the residuals. We can calculate the R square. So that's the proportion of variability that is explained. So the explained variance, it's between 0 and 1, while 1, you completely explain all the variance in the data. There is an adjusted R square that is also shown in R when you use LM. So that penalizes models with many independent variables. So when you run different models and want to compare them, you should look at the adjusted R square. And then there is also the F statistic. So some strengths from regression, it's easy to understand. You can use it with any set of predictors, both categorical and continuous. Some weaknesses, well, there needs to be the linear assumption that needs to be met. It's not always given. Outliers can have a significant effect sometimes. And also multicollinearity is a problem. So when your predictor variables are correlated, then that's a problem. With that, we go to logistic regression. So the difference is now our binary outcome is 0 or 1, true or false. So we cannot use a linear regression because, you know, the regression line will go beyond 1, below 0. So we have like a bound, which is between 0 and 1. That's why we use this logistic function. And with this logistic function, we bound our outcome between 0 and 1, as you will see on the next slide. In R, we can perform a logistic regression with the command glm. And we specify the family here. It's as binomial, and then we have logistic regression. There are other types as well. So this is a part of the general framework of generalized linear models. And then we have here the outcome and the features on the right side. So that's what I had mentioned beforehand. So our regression line would just go beyond 1, you know. So that's why we use this logistic function, which shows here as a curve called the sigmoid curve. And we don't get just 1 and 0. We actually get probabilities. So we get values between 0 and 1 from the logistic regression. And we can then threshold, let's say at 0.05, and say when there is, so that's the probability of an event, let's say for a patient to have cancer. So we can then say when the probability is above 0.05, it's a 1, or else it's a 0. So we threshold the predictive values. And it's important to know that we can threshold them at different spots. You know, this is something where you can exploit. So if you are really interested in sensitivity, in high sensitivity, you might consider to have a lower threshold. For evaluating logistic regression, we have a nice function predict, and we just submit the model and the new data, and we get all our predictive values. So these probabilities I was talking about. And then we can threshold them, create a confusion matrix. We can also do some diagnosis of the model. So we can look at we can compare the residual deviance to the null deviance. So that's a bit similar to the residual sum of squares in the logistic regression. It's a measure of how well your model fits. And the larger the value is, the worse. So smaller is better. Null deviance is you just fit a model with an intercept. And residual deviance is then how well the model did with both predictors and intercept. And the larger the difference is then between residual and null, the better. There is another measure that we will also look at, which is the AIC, the Akaike Information Criterion, which is a quantification of how well the model does explaining the variability, and lower AIC is preferred, like with the residual, the deviance. And this AIC also gives a penalty for if you have a large number of variables. So when you add a variable and you always will explain more data by adding more variables, but maybe the AIC does not favor this model because it does not meaningfully explain more data by just adding that variable. It will always explain a little bit more, but when it's just a tiny bit more, then you can remove the variable. How do you improve the model? So we will then use some techniques to improve the model. We will remove, multi-collinearity. So I will show you how to create a correlation matrix and determine something which is called a variance inflation factor width. And the general rule of thumb is that when the width is larger than 5, that it is an indication of that the variable is correlated. But other textbooks, they name different numbers. So that's a little bit the point of debate. Then cutoff values, I already mentioned that. By default, you can take 0.05 as a cutoff. I just see there is a question. Is AIC a good metric for controlling overfitting? I would say to control overfitting is then finally the evaluation on the test data. But as I mentioned, AIC is penalizing when you add a lot of variables. So with that, I would say yes. But ultimately, the test would be, I would say, to then evaluate on the test data. Strengths and weaknesses from logistic regression. So the outcome is easy to understand probability. And we can also look at the coefficients and interpret the coefficients. I forgot to mention that here. So we get log odds ratios and we can, they are a little bit hard to interpret, but we can interpret the odds ratios, which is just the exponent of the log odds ratios. Weaknesses, it can underperform when multiple or non-linear decisions boundaries exist. So non-linearity is always a problem in regression. Maybe you could add, you could square or take the log or take the square root of one of the variables, let's say h squared, and try to do that. It is vulnerable to the presence of multicollinearity, and it is also sensitive to outliers as well. So with that, I think I have now half an hour of slides. So we are good in time, and now I am open for some questions before. So I will unshare and share my R screen. Okay. So so that's our studio, as I already showed in a picture on the slide. It is not a script what I show you here. So when you create a new file, you have different options. And I used an R notebook. So you remember from the last session where a colleague of ours, he presented Python and Jupyter. So that's a notebook as well. And in R, there is also this feature of a notebook. And the notebook just unites code and output, like statistics and tables and figures, in one document. So that's really nice. And in this notebook, you have sections where you can place some code. And you have also some, yes, so here you can place some code within this section here. I hear some funny noise. Do you hear that as well? No, it's now. Okay, it's gone now. Okay, so, and between the code sections or the code blocks, you can add some text. So that's how the notebook kind of are built up, basically. And I can add also some headers by using Markdown. And then you have here like a table of content with all my headers and subheaders. So I can quickly go to different parts of my notebook. All All right, so let's start with loading the libraries. So first of all, in this practical session, you will learn the first steps in machine learning in R. So data reading, data management, and then also visualization and some descriptive statistics. And then there are two showcases, one with linear regression, with the CDC data on blood pressure, and the showcase with logistic regression using the Wisconsin breast cancer database. Okay, so so you have here a nice play button. So you can just press play and it will run the whole section. So I get sometimes some warnings from packages because they are overwriting some methods that have the same name. So that's important to know. But for our example, you can just ignore that. So maybe let me first explain what is this data set about. So our goal is to develop and improve a linear model to predict systolic blood pressure from a set of variables like age and gender using linear regression. So the data consists of over 1,400 patients with 9 variables. There's also BMI and smoking status. So that's real world data from the CDC. I provide you the link where you can download the data. So the first thing is I read this data. So I have here a block reading data, and I define some colors. That's just for my figures. That's not important. But the relevant variable is this one. The relevant line, here I read the data. So that's a data frame. And the way you work with data frames is I go now here down, maybe, yeah. So CDC, and then I see all the data. I can check the dimension. CDC, so I have these 1,400 individuals. So that's the lines across 9 variables. So I can, for example, also press $, and then I can access the different columns, and that's really nice. So I don't need to remember anything. I can just, select, let's show the systolic blood pressure. So that's our outcome. So here you see all the blood pressure values, or I can just show you, the first 5 lines. So we have here the first patient with a systolic blood pressure of 100, the weight, the height, BMI, waist, circumference, and the age. Then diabetes and smoker status, and fast food. So fast food is a variable where I think it was asked like how many meals you had in the last week, how many fast food meals. So here this patient had 5 meals. Okay, so I can go. So here in this console, you can always interact with the data, and I will now run this whole section. And this command here, I show the first 5 lines, which you can see here now. Here you can see now how this notebook looks like, that you have code and then also output together. So that's really nice. Now, maybe you notice that diabetes is 1 or 0, or smoking status is 1 or 0. So I don't really like 1 and 0 because you can give names. So for example, imagine you have a treatment and a control group in a clinical trial, and you have control is 1 and treatment is 2. So you have to remember that, and that can cause a lot of confusion sometimes. So it's really important to be explicit. And so I usually rename these to, diabetes or no diabetes, or yes or no. So that's it's very clear. So that's just some code to rename that. And now when I look at my data again. With the first, again, the first 5 lines. So it's now yes and no. So you can, an important command is the summary command, which gives you summary statistics across all the variables. So it's quite a lot of data. You have the smallest value, the largest value, so min and max. You have the mean, and you have the median, and you have the interquartile range for all these variables. If you had missing data, it will also show up here as an additional line, NA, and then how many cases. So this gives you a nice overview of your data. You can check, if maybe something is wrong, like when there is in systolic blood pressure, for example, it goes from 80 to 224. So that seems all reasonable values. So it's important to check that. Then the next thing is maybe you want to make a figure. So figure is also really easy. So let's take CDC. Let's take H. So I can create a box plot. And you see that here on the bottom right. Or another variable. And you can also, when using factors, you can also split that by your grouping variable. Let's say smoker. So this will then create 2 box plots, one for the non-smokers and one for the smokers. That's really nice. I, however, use ggplot too, which will look more complicated, as you can see. So I will just run that code. So so I create here a histogram to look at the distribution of systolic blood pressure. We see here some values are quite large, and also some box plots. So, but you can also use the simple R plots, it's much easier. The reason I use ggplot2 is at the end of the day, I can really fine adjust everything. So that's a little bit the price I pay. So I have to write some a little bit complicated code to generate these plots. But the way it is built up is basically you generate a ggplot object, and you submit here the data, and you can specify, what's on the x-axis. And this is like the foundation basically, but this is just an empty plot. And on top of that, you kind of stack or add additional layers, like for example, here an histogram, and you combine that by using a plus. So it's like, the basic plot, or where you define the data and what's X, what's Y, and then plus a histogram. And this will give you then the histogram. Or here it's a box plot. And then you stack this up, like you can also change the theme, the colors, and this, the more you change, the larger it gets. But with that, I can really fine adjust everything the way I really want it to look like. The next thing is we can do a little for loop here to look at the distribution of all the variables. So not just the continuous ones. And then we can look at that. So H is more or less like has a uniform distribution. The others have more kind of a normal-ish like distribution. Fast food is really, really right skewed. So we have lots of people that say, well, 0 or 1 meal And then few people have like 20 meals like every day or so. So in the next part, I want to split the data. And I do that by random sampling, and I take 75% for the training data set. And the rest, so this is my index. So this will give me all the row numbers. So when I do this, I will have all the row numbers that were randomly selected for this 75%. And then I subset here my data frame by selecting only these rows, and that's then my training data set. And the inverse, so all the other rows by using a minus here, will then select the remaining rows. So I run that. So I have now two more data sets, a training and a test data set. When I look, so my overall sample, so this should add up, right? So this one here has now 1,100 patients, and the test data set is 25% is then 369 patients, and this will give me the total. This should equal to n. So what I do here is I check whether everything is correct by using this assert statement. I use that on a regular basis. So with that, I can kind of constrain that things are correct. And this is from the tested package, which I loaded here at the top. And with that, you can kind of check whether some conditions are hold. So sometimes it's even important to check the obvious, because many things can go wrong. So I am here checking that all these things should add up. Then, so I will skip that. So let's now fit the model. I will fit, so the outcome is systolic blood pressure, and I will just use H. Just a very simple model. And I call this fit 1. And this is the output that you get. So what you see here is different parts. You see here the formula that I used, and then you see the residuals. So this is the how off we are. So with one patient, we are off with our predictions by 100. And remember, the residuals are the actual value minus the observed value. So that means that the actual value minus the predicted value. So our predicted value was smaller in that case, because here we have a positive value. So we under predicted this patient's blood pressure by 100 points. So this is important information here. And then we have the coefficients. So these are the beta estimates from the regression. So 0.04. So that means per each unit change in age, which is 1 year. So for each additional year, I have an increase in systolic blood pressure by 0.04. And we have a standard error as well, and a test statistic. So yeah. Then we have the residual standard error. That's like the standard deviation of our residual. So we are off by 16 points in average. We explain about 16% of the variability in the systolic blood pressure. So that's not great. And here we have a F statistic, which is like, is there a relation? It's an overall test. Is there a relationship between our predictor variables and the outcome? And this is highly significant. but we do not explain a lot of data. So 85% is unexplained data. Okay, so maybe we can do a little bit more looking at the residuals. So I can access the residual. So as I fitted the model, I got this fit one. So that's an object. And here I can access all my residuals. So these are all the errors. And so here I can sort them. And here we see our biggest one. So this is this 100 points where we are off. I can get the line where this patient is to look at the data of that patient where we are so much off, you know, to see what happened here. And I can also then look at the blood pressure of this patient. So this blood pressure had a value of 224, but we underestimated by 100 points. So our fitted value is 124. So that's here where this 100 points of error came from. So it's always interesting, you know, to look at the residual. It gives some important information. Maybe there is something special about that patient, you know. So that's certainly interesting. So let's now do another model. So let's now fit all the variables, because we did not explain a lot of variability in our systolic blood pressure. So here I fitted all the variables, and you can see which variables had an effect in terms of statistical significance. So all the ones with the stars seem to have a statistically significant effect. So it's age, it's weight, and it's the BMI as well. However, we did not really improve, just a little tiny bit. Now we are at 17% of explained variance. So the next thing is as I said, it's important to check the residuals. So they should be normal and mean zero. So I do a plot here to look at that. So that's the residual from our second model, okay? So that looks quite okay, and they are mean zero. And here is to test the heteroscedasticity. So here we look at the fitted values, and along the x-axis, so this is the systolic blood pressure, and the variability of our residuals does not change along that fitted value. So that's good. And here you see our data point with 100 again. So these patients where we were by 100 points off. Okay. But you might have noticed that some of these variables, you know, they are highly correlated, like weight and BMI, so, and height probably also. So we should look in the next step, we should look at the multicollinearity, and we do that by creating some correlation matrices. And we can see now, as kind of expected, that BMI is correlated with waist circumference by correlation of 91.91, and also with weight. So that's not great, and we have to take care of that. Also, we can have another measure, the variance inflation factor. So we could just use this function. And remember, when it's higher than 5, though there are other textbook recommendations, then we have a problem. So weight, height, and BMI is all above 5, also waist as well. So with that, I will now do the following. I will just fit a model of H, because that seems relevant, and weight. So H, BMI, and weight is correlated, so I will ignore them. And diabetes and smoker status doesn't seem to be that relevant, so I will also skip that. And our next model is just, so model 3 is just with 2 predictor variables. And here we have our results. So, but another thing is that this result, I don't really like these results. So when you report your effects, usually use a confidence interval, not a standard error. So you can create, so let's do it with H. So with H, so the point estimate is 0.04, and then you can calculate the upper, the lower limit and the upper limit, which is a range where the point estimate is likely to be. So that's our confidence interval. And there is a function that you can use. It's from our biostats UZH package that I load at the beginning, table regression, which gives you a nice table with the coefficient and the confidence intervals. And the p-value is also like nicely in a nice format. You know, this is not really a nice format here. So that can be useful to generate nice tables for publications. The next thing I want to show is a inferential point analysis. So here I will identify some points. So that's a technique to identify some data points that are off. So it's based on Cook's distance. And I call this Cook's distance D, which reflects the sum of all the changes in the regression model when an observation is removed. And there is a formula for a cutoff value, which you can see here, and I can use that and make a plot. And you can see that all these values above this line, they are kind of outliers or influential points. And I could try to remove them, for example. Whether this is a good idea or not, we will see. But let me just do that. So I have here a new data set, which is CDC train, but with exclusion of some data points. And this is actually about 5%. So I will exclude all these points here that have too large of Cook's distance and create a new data set. And I fit the same model now. And now I have a little bit increased our explained variance. So we are now above 20. We are at 21% of explained variance. So that's an improvement. It's not great still. I mean, 80% or 79% of unexplained variability in the data still. So we need more variables, I would say, but that's the data set we got. So I can again do a nice table with the confidence intervals. So the next step is I want to compare these models a little bit. So with the AIC, you know, and remember that the smaller the better. So I will compare here the first, second, and third. And let let's have a look. I cannot compare the fourth one. Did I have a fourth one? Yeah, the fourth one was the one where I excluded some data points. So because this is a different data set, it's less data. I cannot compare it. I have to have the same amount of exactly the same data, but different models. Then I can compare it. So, but here we can see that this one is the lowest. So model 3 is the best in terms of the AIC. So model 1 was just age. Model 2 was all the variables, and model 3 was just 2 variables. So that seems to be the best. So what I can do now, I can use now this model to do predictions by using the predict function. And I will just have like a new patient and predict the systolic blood pressure for that patient. So let's say that patient is now 74 years old, has a weight of 74 and the age of 41. And keep in mind, we zero meaned our age. Oh, wait, did we do that? I think we didn't do it. Yes. So I go back up where I did the first model here. So yeah, the reason I did mean 0 age is because I forgot to explain here this more properly. So the intercept is not really, I think I did interpret the estimate for age, but not the intercept. So the intercept, you interpret the intercept as the systolic blood pressure when age is at 0. So that's not really meaningful because 0H doesn't really make sense. So here I mean center the variable age, and then we can interpret the intercept, right? So that's now our first, that's now our model. Okay, so with that, I can now go back. And when I do the prediction, so that was prediction of a single data point. So that's why here I have to subtract mean age because I did this transformation. And now I predict here a blood pressure of 100 for that case. And in the next step, I can actually predict all my test data set by using model 3. And I get now all the values. So for example, you can see here now my predicted values, which are here. And then the actual value. So for example, here the actual value was 124 and we predicted 29. But because I forgot a section, let me just run all that code again until here. So I can show you how you do that. I could, remove all the variables and then press here, which is run all chunks. Because maybe there was something different. Maybe something was wrong because I did not run that block at that time point. Okay. So yes, so I think the fitted values are a little bit different. So that are the correct values. So here, for example, we are pretty close. So this was 138 and we have predicted 134. But to make an overall assessment, I will now calculate the root mean square error and the R-square. And this is now with the test data. So that's the ultimate evaluation test. And we have here a root mean square error of 16 and the R-square of 17% or almost 18%. Now the question is, what happened? What happens when we use the model that has been trained on the more clean data, where we remove these influential points, and this is model 4. We had there with a R square of, I think, 20 or even a little bit higher, 21%. So I will now change here to model 4. Okay. And it's about the same. It's even a little bit worse by 1%. So from that, the exclusion of the outliers didn't really help. And outliers often are irrelevant data that need to be considered and cannot just be removed. There might be situation, you know, when you have a really messy training data set and a very clean test data set for some reason, but that's not the case here because we did a random sampling. So here I just wanted to demonstrate that this exclusion of these outliers didn't help. So with that, I came to the end of this first data set, and maybe just a few things. You can add more variables that would certainly help here. Clinical knowledge is always important when it comes to variable selection and model development. It's not right to just press a button and then are there nonlinear relationships? Maybe H is kind of not is related to systolic blood pressure in a nonlinear way. So there is room for improvement, and we can look at these sorts of things as well. For example, also to look at interactions. Okay, so are there questions? Like apples and oranges. So I would have a hard time to interpret the coefficients. So that's why I do this scaling here. Then I split the data just like before. But now I have a little bit of imbalanced data set. So when I look at data, no, that's cancer, that's the data. And here is then the outcome is the diagnosis. See, it's imbalanced. Okay, so I do a resampling and make it a balanced data set, but just a training data set to train the model. And now we have equal amount. Now with all these techniques, it's important to check the data, like also when you do multiple imputation to address missing values. So what I'm doing here is I make some plots where I can see, so that's the original data set where the red ones are the malignant tumors, and that's the minority class. And here is the balanced data set where I basically imputed or sampled more of these patients. So here it's much more red points. So now it's balanced, but I check here whether something weird happens, but that looks fine to me. So the distribution is the same across these two variables. And I check that across multiple variables. And from that, I would say we can proceed. However, we have 30 variables and there is a lot of correlation. So I make a correlation plot and check all those who are highly correlated and remove them. And I do a very basic technique. So this is something that needs to be discussed with a clinician, that's for sure. So here for this tutorial, I just do, remove all the ones that are correlated, and then I have a cleaner uncorrelated data set. And when I do the correlation plot again, I don't see any correlations anymore above 0.6. So that's fine, I would say. So with that, we can proceed to run the model. And I did run a first model here with all the variables. And I will not go into detail, but as we can see, some of the variables seem to be important. They have a statistical significant effect, but others, they don't. So from that, I can also look at the AIC, so the importance, and I can see here that the most important variable seems to be the area mean, which is also consistent with this high set value. Now, just that I can compare two models, I will create a model with just area mean, just a single variable in the logistic regression. And with that, I have now two models that I can test on the training data and create a confusion matrix. So here I have the confusion matrix. So I have, so this particularly concerns me. So we have 6 cases where there is a malignant tumor, but we predicted 0. So that's false negative, right? And then I can calculate now the sensitivity and specificity, which is 89 and 95. Now let's check our second model. And here it's a little bit worse. We just used one variable, the most important one. And here we are a little bit worse. And what we can do is then create at the very end, we create a receiver operator characteristic curve, and we can compare these models across different thresholds. Remember, we just use 0.5, but we can also use 0.2 as a threshold or 0.9. And here we can also compare these two models. And I would say model 1 is clearly to be preferred because it has a larger area under the curve. The best would be 1. And if the prediction is purely random, it would be here along this line, the diagonal, and it would then have an area under the curve of 0.5. So with that, I came to the end of that second data set and the practical session.